So this is our fourth presentation, overview of the KINEROS2 model, and I'd like to talk just about some of the major components and limitations. So the KINEROS model started, I don't know, 60 years ago with David Woolheiser, and then evolved with various graduate students of his. And we've kept it going, and our lab is the primary developer, and we improve KINEROS as people use it. So it's been used a lot. It's been around a long time. So it's pretty well debugged. Now, should mention, if it hasn't been already, that SWAT was developed by the ARS lab in Temple, Texas. And, just like we are the main developers of KINEROS, they're the main developers of SWAT. They'll have more current versions. They've got a version of SWAT that will use QGIS, for example. SWAT, it's a good model. It's right for a lot of places, given the data availability. However, in AGWA, we are defaulting a lot of the inputs to make SWAT a little more user-friendly and easier to use. So we can talk more about that later if you'd like. The KINEROS2 is a distributed kinematic wave runoff and erosion model. And again, we'll give you some background, model features, talk about sensitivity, flood forecasting, and limitations. And the diagram you see at the top right is an actual set of small subwatersheds within the Walnut Gulch experimental watershed. So we've got, on the discretization, we've got two channels leading into one, and upland area on two of these. So that gets abstracted into this sort of configuration. Now we're showing the model or the hill slope elements as overland flow plains. They can be curvilinear. You can also vary the width, increasing it downslope or decreasing it downslope. But this is the basic configuration where they're emptying into a trapezoidal channel. So we saw this slide at the beginning in terms of the configuration. Again, this is only a single channel, and we are making a distinction between left and right side. It's an event-based watershed. That's what's available in AGWA now. We do have a continuous version of KINEROS as well. Requires some more inputs. It has not been integrated into AGWA yet, but if you're interested in that, please contact us. So again, it's physically based with dynamic routing, both for overland flow and erosion, and this might be misleading. It's kinematic routing, but dynamic means there's interaction at every computational node and at every time step that's tracking water flow from upslope, from rainfall, as well as infiltration to give you an estimate about what's going downslope. We've used it in urban environments. Phil showed you that in the last example, and you'll see another presentation tomorrow that Yoga developed a individual urban element, I'm sorry, twisted tongue, a urban toolkit that's an add-on to AGWA. And again, that will allow you to model down to the lot level and see more about that tomorrow. Again, we're looking primarily at hydrology, erosion, sediment, and nitrogen phosphorus with an opus version of KINEROS. And again, that's something you'd have to contact us about. It is not currently in AGWA. It's typically applied to smaller watersheds. And as Shay noted earlier, you can apply it to larger watersheds, and it has been. But we kind of use this figure because this is the scale roughly of the Walnut Gulch experimental watershed. And that's one of the few places we feel we have sufficient data to really validate and verify the model up to those scales. As I say, we've applied it to much larger watersheds in a relative change analysis, but there's more computational time involved once you get thousands of elements if you want to keep them relatively small. So here's another kind of representation of the abstraction process. You're approximating the watershed with these overland flow elements, channels, and impoundments. So this is subwatershed 11 in Walnut Gulch. There's a stock pond at the end of this element labeled pond catchment, and it rarely spills. So we typically model it and say there's no runoff out of this. And then we take the remaining area and again, look at the contributing areas to the channels left and right across here and the upland flow elements. And again, that gets abstracted into the diagram that we see here. And again, these are rectangular overland flow plains. They don't have to be rectangular. And they can be curvilinear, but this is the idea of the abstraction. You're turning, by doing this, you're basically turning a two-dimensional problem into a one-dimensional flow routing problem, which simplifies a lot of the computations. Oh, sorry, I want to back up again. Want to mention we also, if you do have multiple rain gauges or radar rainfall data, built into this is a space-time rainfall intensity interpolator. And this on the fly does interpolation to the centroids of the individual elements. The centroid of this would be here. And I think we have a diagram further on down that will show you that in a little more detail. So there are a number of types of K2 model elements. Again, we've got this overland flow element for contributing hill slope areas. Again, planar, curvilinear, and you can also do cascading plains where you might break this into two if you have, that's a Walmart parking lot at the top and an infiltrating area down here where you have distinctly different characteristics of the upland area. We typically use a trapezoidal channel. That's the default, but we can do a compound channel, and we can also do natural channels now that either have been surveyed out in the field or extracted from LiDAR data. These gives you a better representation. And again, Shay, just quick question: there's no switch or anything for the LiDAR data, is there? It's just a TIFF file?
No, yeah, it just is consumed just like any other BEM raster. Okay.
And more LiDAR data is becoming more widely available, and you probably know there's a national program going on by the Geological Survey to get LiDAR data over CONUS as well as Hawaii and Alaska. We've got an urban element, and this basically turns an overland flow plain into segments, and where you have pervious area running off into a street, or you have impervious area, and you have the combinations of impervious, like a roof, flowing onto the front yard and then onto the street, or the other combination of impervious pervious to impervious. So this is the concept that Yoga improved upon that you'll see in the urban toolkit tomorrow. We've got pond elements. What you need is the geometry of the pond. So you basically need to know the volume and area of the pond. So again, that's often done with field survey and also can be done with LiDAR. And you need an outflow rating. So as the water level gets increased, If there's a outlet weir or even an overflow bank, you need to know that. And then we have this thing, an injection element, where it's just basically you can insert this between any element. And you might use this in the case where you actually have gauged discharge data, observed data at some midpoint in the watershed you're looking at. And you can take the observed hydrograph from the gauging station and inject it into the model network downstream of it. And so just talk a little bit more about RHEM. So we have two basically erosion capabilities. RHEM is integrated with KINEROS for management applications, again, primarily on rangelands. There's another older erosion equation that is a little harder to parameterize than RHEM is. And again, AGWA allows you this geospatial interface. And this is a slightly different depiction of the flow diagram or the workflow diagram we saw in the first presentation, where we have chosen an outlet, discretized chosen an outlet, which gives us the outline of the overall watershed. We've discretized it into modeling elements. We've intersected the polygons of the modeling elements with soils and land cover. And then we can force this with a storm, observed or designed storm, bring in the results and display them in a color ramp fashion. So what does RHEM do? Again, it estimates runoff, erosion, and sediment delivery rates at the spatial scale of a hill slope. And again, this was designed to be a calculator. There's a web version of RHEM, which just looks at a single hill slope. You can put in various soils parameters. You can put in the climate from long-term reference networks, and you can define the shape. So that's been integrated into KINEROS as sort of the engine for our hill slopes. It was designed specifically to utilize data that's collected by NRCS, the Natural Resource Conservation Service, in their National Resource Inventory database. So that data can be brought in directly into KINEROS, which is field data collected from tens of thousands of points across the country. And as I say, from a research purpose, this is a way to bring in new science, particularly in terms of rangeland infiltration, runoff, and erosion. So WEP is another model developed by ARS and that is used by NRCS. And that's really designed, WEP is Water Erosion Prediction Project. WEP is really designed for cropland situations where you have tillage and mechanical operations of the soil. And it looks at different cropping patterns, applications of fertilizer, pesticides, that sort of thing. So another kind of neat algorithm that Dennis Flanagan, we've got the paper on this and it's on the website too, is how can you get a representative slope and flow length profile? So again, this is an aerial photo here, and imagine you're at the top of this hill slope and you're looking down to the channel. You might measure the length and the slope along this one flow path, but this entire area contributes to the side of this channel. So there are many flow paths that will go down a single overland flow modeling element. And the method that Flanagan came up with basically looks at all of the elements contributing to a channel. These are all hill slope elements. And you'll notice some flow paths are really short and some flow paths are a lot longer. And what this method does is traces all of the flow paths from the top of the element down to the channel. And while it's doing that, it's calculating a weighted grid for each of the hill slopes for slope and for flow length. And basically what it gives you is a calculated weighted length for each path and a slope for that flow path. And the nice thing about this is, most slow or hill slopes aren't overland flow plains. There's something like this, and often you'll have a toe slope that's flatter. That's where a lot of sediment deposition may occur. So this is an option in AGWA. It takes a little bit of computational time, but we feel it gives a much more realistic representation. And here, shows you some of the comparisons and how different they really are. So we had one of our graduate students basically do the exercise of tracing both the length and the elevation change down this flow path with ArcGIS. And, if you follow this path down, you get a flow length of 45 meters. And you get slopes that are much, much shallower than the method we showed on the previous slide. So they are quite different. Again, can make a big, maybe not such a big difference in terms of the total runoff you might get, but it can make a big difference in terms of sediment coming off the hill slope. We also have a diversion element. So think about a place where, and this actually occurs a lot, if a person goes into, or a developer goes into a area and it's got a wetland, and typically wetlands are relatively flat. They have often a lot of vegetation in them. And they're often very effective at filtering out sediment as well as other pollutants. And if you're taking one of these when you're developing, EPA or whatever the regulatory authority is, say, no, you have to replace this with a constructed wetland. Again, and that might be multiple ponds where the water's coming through. So you often increase the flow length. And again, that will lower the slope, and you'll often increase the hydraulic roughness. So what we can do is take a given element and say, all right, I'm going to select a channel that's been represented by AGWA, and I'm going to change its characteristics. So this is the old element, and this is the new element identifier. And here's the information about how the characteristics change. So we're going to make it wider, we're going to make it longer, we're going to decrease the slope, the hydraulic roughness in the manganese is going up, so it'll be much slower, and we can either change or maintain the hydraulic conductivity and the suction terms. So again, this is a handy way to try to represent these cases, which frankly are much more common in more humid regions. And what this representation in sort of taking the elements and putting them into these one-dimensional model elements is you sort of take apart the watershed and put it into pieces. So you can do a lot of things to reconfigure this and to better represent your actual watershed. So again, we might split one of these overland flow elements. In this case, we've got 69 flowing into 71. And again, this might be an infiltrating area, a field going into an urban area, distinctly different infiltration situations. Same thing here. Could be a distinct change in slope from 70 to 73. We can add in another channel if we feel, and create more elements, if you will. And 21 here is again one of these injection points where we can inject a known discharge or hydrograph that can go into a channel and then into a pond element. So there's a lot of ways you can move these things around, still get a representative of the watershed. And that's again, the model elements again are mapped back to the watershed, and that's how we again bring the results out of the computations, runoff erosion computations, and this element, and again can do a color match back to its original location. And this is an example. KINEROS was one of the first models to do interactive infiltration. It's more common now, but in older models where they did just rainfall excess, they would often take the hydrograph and then apply some method of abstraction and subtract out the infiltration from the hydrograph and typically just route that water down an impervious surface. And in KINEROS, as I say, every element is broken into a minimum of 10 computational nodes and a maximum of 20. So at each one of those computational nodes, it's looking at the rainfall, it's looking at any upstream contribution, and it's looking at any losses to infiltration. And so it continues that calculation all the way down to the bottom. And again, this is critical, as Phil showed you, for channel transmission losses that we see in the upper corner here. Again, this is sort of the frothy front of the runoff going down a dry channel. Another thing we can do is represent small scale spatial variability of infiltration across a slope. So this is the scale of infiltration. Think about particularly around here, where you often have desert brush. And so you've got brush and you've got interbrush open spaces. And under the brush, you typically, because of leaf fall, you get organic matter that actually enhances the infiltration of the soils under the brush. Meanwhile, between the brush, I should get a photograph of this, you often get erosion pavement because there's really nothing to slow down the flow, and it'll carry a lot of the fine sediment with it. So this is represented by a coefficient of variation, where you're not just putting in a fixed value of saturated hydraulic conductivity, but a mean value and a coefficient of variation. We're assuming a log normal distribution. And we also can represent microtopography. So, imagine, and again, this is sort of the topography that, again, you see walking across a hill slope. It's not very large. But what happens is, if you represent the topography of a hill slope as a glass flat area, all of that area is infiltrating all the time. And what we find is that after the rainfall stops and you've got a recession going on, you start concentrating flow in the microchannels. So when it rains, it's raining over the whole hill slope, and you've got infiltration going on here and here. When it stops raining, it's only going on over this area. So this is a way to reduce the wetted area, if you will, and we find this does a lot better in terms of representing recession characteristics. We've got a 2-layer soil profile capability. And this is just an example in how the model would respond differently. So in the deep soil case, we've got 0.5 meter, 500 millimeters of, nice, relatively porous soil. And underlying that is fractured rock that has a very low conductivity rate. And then we contrast that to a shallow soil situation over, again, this hard, less permeable rock. And so here's the rainfall pattern that we're applying to these two cases. And, as you can imagine, particularly over here, the shallow soil produces a lot more runoff than the infiltrating soil. And this is a way to also allow runoff generation by saturation excess flow. The default is Hortonian flow or infiltration excess flow, where if the rainfall rate is greater than the rate of infiltration, you'll generate overland flow. So this allows you to mimic both processes. And we also have a version, and had to put this in for the interstorm case, using the Richards equation, which allows you to have basically 10 different computational nodes vertically, so you can represent different layers of soil. However, again, you add in complexity, you add in more information in terms of that you have to gather for input information, as well as typically more computational complexity. We've got a compound routing channel geometry. In many cases, you won't have just a trapezoidal channel. The default one just would go down like this and then continue up like this. You often have out of the main channel kind of an overflow area that's still in the ancient floodplain. And the nice thing about this, most models will handle, particularly flood routing models, will handle a different roughness value in both the main channel and in the side channel or overflow channel. You typically have a lot more vegetation. So this would have a higher roughness value than over here. But this overbank representation, you can also have a different infiltration rate on the overbank channel as well as in the main channel. And this again is a little representation of the urban modeling element. And again, you're breaking up an overland flow element into pervious, impervious, flow on and flow off situations. And this watershed that Phil showed you earlier is a small subdevelopment in the Sierra Vista area. And again, Yoga took this and improved upon this concept to allow modeling at the lot level. In terms of sediment transport, the older representation we have can use up to 5 particle class sizes. And again, the particle class sizes are non-interactive. It can look at entrainment by raindrop impact and hydraulic shear. The wet model is formulated this way. The RHEM model uses a stream power formulation. And again, that is also incorporated. So basically, you may have sediment coming in. Again, this part is your, hill slope flow element. You've got flow going across it. You may have upstream sediment coming in. And this is the ground. You'll have entrainment by raindrop impact or shear or stream power. If the slope changes, you'll often get deposition. So again, this is all done interactively in the KINEROS model. And again, these are the partial differential equations that basically try to represent both erosion and sediment. And the different cases, this is channel, or C is concentration of sediment here. Q is the overland flow rate. And then we've got a splash and sheet erosion terms that add in here. And again, we've got references of all of these. They're in the website as well if you want to get more information on those. So we've got all these parameters. Again, you add in model complexity, you need more inputs. So first we need geometry information, and that's what we get from the DEM data. So we need information about position, length, slope, and width. Then we need hydraulic roughness or flow information. So we need, this is estimated both from soils information and from the literature. So again, we only have DEM data, we only have soils data, and we have land cover data. So we have to get all of these parameters that you see here out of those three data sources. So this is where we develop lookup tables, either from experimental data or the best literature we have. So now we also need, again, infiltration data, and that's the saturated hydraulic conductivity, the porosity, suction term, rock, and there's a residual and maximum fillable porosity. A lot of these are reduced to the effective infiltration value for RHEM. And again, this is from, we give you our initial estimates. AGWA produces basically all of these parameters given those three input types, DM, land cover, and soils. It's our initial first best guess at what these should be. And by no means are they exact. And this is where, if you got local data and local knowledge, you can improve these estimates. Again, erosion parameters, some of these are very hard, and there's not really good field estimates or field techniques to estimate them. Cohesion is one of them. How sticky is the soil, and clays and whatnot. And again, that's simplified in the RHEM model. And again, experimental data and literature. We need channel parameters. What's the shape, slope of the channels, culverts as well, shape, and storage characteristics of structures and urban elements. So this is what we do based on, again, there are three main input types. We take the main soil texture classes that we see listed here, and again, there's a fair number of data out there on, if you have this texture, this is your hydraulic conductivity and the values for the various other infiltration related terms. And there's different methods to do this. Again, we use a technique that was developed quite a while ago, and from lab data for all these different soil textures from samples, over a wide area. And then from land cover type, we need to get things like interception, percent canopy cover. We estimate the Manning's roughness from this, and the fraction of impervious surface. In the newer, in the newer GAP data, they have classes of low, medium, and high intensity. Whereas I think it may have been improved now, but the old NLSCD data just had one class. And again, these are the major vegetation types. We're not trying to, break these things into how much in a single element, how much of it is a shrub, how much of it might be deciduous or herbaceous grasses, and that sort of thing. And feel free, I'm sorry, I should have mentioned this earlier, probably should have mentioned it this morning as well. But, if you have questions, again, put them in the chat, and we'll take those up as soon as we're done with the presentation. So here's a piece of an urban area, and this is an aerial photograph, I believe, and we have to turn this thing into a classified image. So again, we've got a nice park here, or set of parks, a lot of green space. We've got, railroads, streets, impervious area, subdivisions, big airport here. And so there's a lot of assumptions that go from this image into this classified image. So the GIS data has uncertainty in it, as Phil mentioned. So, again, we make a bunch of assumptions to get an initial estimate. So again, consider them initial estimates that are by no means quantitatively correct. But again, in the relative analysis case, we believe, and I think we verified this with, a lot of observed data, that the model will go in the right direction. So, if there's more impervious area, you'll get more runoff. It'll come off faster. So that's why we feel, even with all these assumptions in here, we can do relative change analysis and get useful information out of it. So we've got a version that also does flash flood forecasting. We worked with the National Weather Service on this, and here's a typical radar chase. This is the same stuff you see on the weather segments of the nightly news, the Weather Channel. And each of these pixels is color coded here to an intensity in inches per hour. So basically, the center point of each of these pixels that the radar is sensing are treated as rain gauges. So again, we're intersecting multiple rain gauges, if you will, to the model element. And we can figure out a weighting scheme if 40% of this pixel is in this element, 60% in the next element. We've worked all of that out, and you can get a trace, or a new Doppler radar trace, or estimate of rainfall, about every 3 to 5 minutes. So the Doppler radar starts at a low level and then makes a scan and then spirals up to go to a higher level, and all that data gets integrated. And again, you could calibrate the model using archived radar data and discharge at forecast points. But these color codes here are basically warning levels that the Weather Service would issue based on stage. And every time a new scan comes in, you're basically able to take another time step in your prediction of runoff and flood rate. And then you can continue the model and run it and see where the flood levels might be with the rainfall up to a given point. So this has been tested in about 5 or 6 of the forecast Weather Services offices, and this was really put in for a need to look at fast responding basins. And again, you probably heard about dangers or issues in Zion National Park, where they have all these slot canyons, in southern Arizona as well. And you may be completely dry where you're standing, but there may be a rainfall event upstream. You don't even see the clouds, and you get a very rapid response. And the older, the river forecast models are getting better now, but they typically had a time step that was sometimes 6 hours for big rivers. That's been replaced now by the National Water Model, which is getting things down to a finer time step. Sensitivity. Excuse me, get some water. And this is, what are the most important things to try to either get data on or to adjust model parameters? And as Phil showed you in the last presentation, rainfall inputs, most critical issue. Now, this may not matter in a design storm situation because it's specified, but in a real world situation, you don't get the rainfall right, you can't expect to get any good predictions. Next are things you can have control over in terms of adjusting the saturated hydraulic conductivity and the hydraulic roughness. And again, as Phil noted, these are all a function of watershed geometric complexity. But if you don't want to turn, play around and turn a lot of knobs, these are the two parameters that you'll concentrate on. And this is just an illustration that, again, you can't necessarily make the assumption that a small watershed has uniform rainfall distributions over it. So this is that small Lucky Hills watershed we saw in the very first title slide. And there's a watershed here, and then the intervening area. For studying this, one of their graduate students out, this is 4.4 hectares or about 10 acres, put out 40 non-recording rain gauges, 9 recording rain gauges, and this is one of the events that was recorded. So this is total depth, but you can see it goes from a low level of about 45 millimeters up to, what do we got, 56 or 57 here. And again, average of 52, but a range of 20%, 10% on either side of this value. And that makes a lot of difference in this small watershed. Now, if you have a big watershed, a lot of this variability will get washed out. But here we've got 5 recording rain gauges in these Lucky Hills watersheds, and we're modeling the runoff down here at the Flume. And if we input this data from each of the 5 rain gauges individually, this is the kind of variability. So on the low end, you'll have a 10 millimeter per hour peak and a high end about 27 or 28. So the point being, if you're going to model at this small scale, you should know something about the spatial variability of rainfall at this scale. Now, what we found, and I'm sorry I don't have the slide, but if you use that spatial interpolation scheme with all 5 gauges, you can do a very good job predicting the observed runoff. And so another one of our students, graduate students now, works with NASA, really took a look at all the parameters in KINEROS. So here's that subwatershed 11 again. Here are the red dots are rain gauges, both in and surrounding watershed 11. And, these are, again, the different sorts of elements and observational data. So he looked at both rain gauge data as well as radar data. Again, not a very big area, 6.5 square kilometers. And you've got almost, when you look at the soils and the land cover data, almost homogeneous parameters are initially estimated out of AGWA. So he went through Monte Carlo simulations in which the 23 different parameters were modified using a multiplier to move that parameter up and down. The assumption being that the soils and land coverage data will give you some idea about the variability across this watershed, and these multipliers scale those differences up or down. And in the literature, they call successful forecasts that go into the behavioral envelope. And some, depending on how the Monte Carlo depicts the parameters are well outside what would be considered a realistic simulation. And here's what you get. So here's the multipliers. So here's the multiplier on the planes are the overland flow elements, saturated hydraulic conductivity, plane roughness multiplier, and then again on down the line of that of what I showed you, and then you got rainfall down here. And basically this looks at the influence of uncertainty in the estimates of peak magnitude. So the red ones are a first order effect. The blue are, total effect. Blue are a first order effect, and black are first and second order. And so again, if you don't get the rain right, you're going to have all sorts of uncertainty. And this is similar to the bands, if you will, that Phil showed you on that small watershed in Sierra Vista. So this is discharge, cubic centimeters per second versus time for an individual event. So again, here's the actual observed hydrograph, watershed 11, and here are the confidence intervals. So again, there can be a lot of uncertainty in here, but notice the high value of the y-axis, 16. So now this graph puts in both model and parameter uncertainty plus rainfall uncertainty. So, these bands now go from basically 0 to 100, and they only go from 0 to 15 or so in that case. So this again is an indication of the relative uncertainty and what are the important parameters when you try to calibrate them up. Some additional limitations: KINEROS cannot do backwater or pressurized culvert flow. So, if you overtop this culvert, get a bunch of water over it, you've got pressurized flow, and typically you need a higher order diffusion equations or the full dynamic wave equations. So what could possibly go wrong? And as you can see, plenty. So again, we're not trying to say these models are worthless, and I hope you don't take that away from this presentation. But we want to be realistic in having you understand some of the issues with these. Now, some models that may be sold or promoted by consultants or whatever may say, this is the greatest thing since sliced bread, and it'll make great predictions. And if it sounds too good to be true, it is. So we've got the kind of errors we see here. Is the model conceptually correct? We wouldn't apply KINEROS in Florida, for example. There's groundwater. It's very flat. It's just the wrong type of model. We can have programming errors in all of these models. We might have poor process representation in terms of how we think the dynamics of a particular process work. So we saw we've got errors in classification data and GIS data. And again, we make all these assumptions in the lookup tables to give you these first guess initial estimates. Okay, then we can have processing errors. Again, the early DEM data had a lot of issues. It had a lot of artificial pits and this sort of thing that would, give you a very complex and unrealistic watershed. Those have largely been cleaned up. They're much better now. And again, lack of input data. And AGWA may fail to characterize the watershed properly, again, with just that limited information, DEM, soils, and land cover. So just wanting to make you aware of all of these things. And use the model, but use it responsibly. So what are some of the strengths or weaknesses of KINEROS? So we can use readily available inputs. Again, these are nationally available. It's physically based. It has high resolution in both space and time, can simulate flood routing, and can simulate sediment budgets. The weaknesses, again, anytime you get a more complex model, let's say going from SWAT to KINEROS, you got more parameters to estimate. And again, it's currently in AGWA. KINEROS2 is not continuous. We're working on getting that into AGWA. The subsurface flow component is weak. The best we can do is set a base flow component, but again, that's not static. We do have a recently developed snow model for KINEROS that is going to publication soon. It looks very promising, and as Phil said, KINEROS, as well as he said, any model will not model small events well because of the inherent uncertainties in the inputs. So our conclusions. KINEROS2 evolved from a research model to one that I feel has gained quite wide acceptance. It's very sensitive to rainfall inputs and infiltration. In a water limited environment where we have these small runoff to rainfall ratios, it can be very difficult to model these, and it's highly dependent on very good quality input data. And the model representation has to keep up with changes in the watershed. So again, this is where, if you're evaluating fire scenarios or a change in land cover or urbanization, and you'll see we've got some tools. We'll have another presentation, I believe by Phil tomorrow, that we have tools to change a piece of land, to draw a polygon around it and say, this is no longer a natural piece, this has been urbanized, and a way to represent those things. So again, you'll see more on this tomorrow, and that's all I've got.